All right, in our fifth and final lesson of this unit, we are going to be finding the areas of regular polygons. This is by far my favorite lesson, which typically doesn't translate to you enjoying it that much, but I do think it's fun because it's the culmination of all the hard work that we've done in this unit. And so we're kind of putting all those pieces together with special right triangles and Pythagorean theorem and simplifying radicals and area of triangles and kind of generalizing our previously understood geometric concepts. So this is very good stuff. Our focus is going to start with regular polygons. And so in order to focus on this, we need to know exactly what regular polygons are. If we're going to find their area, then we need to know what a regular polygon actually is. And so thinking back to Unit 3, we recall that regular polygons are those that are both equilateral and equiangular. All right? So that means that the sides are all congruent to each other. The angles are all congruent to each other. Now the angle part is really important, but so is the side piece. All right? The part about the sides being congruent there is helpful because if we know the length of one side, then we know the length of all the sides, and therefore we know the perimeter, and that's going to be an important part of our formula. Also, the angles are going to be useful to us today because in a couple special cases, we're going to be using special right triangles to kind of further our case and to try to find the areas of these figures. And so part of that process of understanding the measures of those angles at their vertices is to remember these two formulas from back from Unit 3. The sum of the interior angles is n minus 2 times 180. And therefore the measure of each one of these angles, since they're all congruent, is that total divided by n. You will probably have a little bit more enjoyment if you can recall that the measures in an equilateral triangle are all 60 degrees. In a regular quadrilateral, they are all 90 degrees. In a regular pentagon, they are all 108 degrees. In a regular hexagon, they're all 120 degrees. That information is very, very useful to us. All right? And so that's what you get when you take n minus 2 times 180 and then divide that total by the number of sides, which again, the number of sides and the number of angles is the same number. All right? Just keeping that straight from Unit 3. This was long ago. We did that. We're in Unit 7 now, so this took us a while to get from there to here. And so the next thing that I want for us to understand is understanding radii. All right? The radius of a polygon is that distance from the center of the polygon to the vertex, or to a vertex of the polygon. So any one of these dashed segments from the center is referred to as a radius. All right? It's the center of a circle that circumscribes or is circumscribed about that polygon. All right? Using some fancy pants geometry language. You don't need to know that. The key here is that the radius of a regular polygon is that distance from the center to the vertex. All right? Now, that carves out some angles there at the center. Those angles at the center are referred to as our central angles, those angles that are formed between consecutive radii. All right, by consecutive radii, what I mean are these right here. All right, so between consecutive radii. And now each of those, we find their measures by taking the total 360 and dividing it by how many radii there are. All right, how many pieces did this one get cut into? Well, this is not a surprise. This six-sided polygon has these 6 radii drawn. And so each one of these angles is found by taking that total of 360 and dividing it by 6. Back here on the square item, we would have 360 divided by 4. This would be 360 divided by 6. Each one of those angles would be congruent. All right? And so each one of those measures 60 degrees in a regular hexagon. In a regular square, in a regular quadrilateral, those would each be 90. In a regular triangle, an equilateral triangle, we would call each of those central angles 120 degrees. All right? And so that's going to vary depending on how many sides we have. The number of sides, the number of vertices, the number of radii, all the same number. The other thing that happens is that this radius also bisects this opposite angle here. All right, or this angle at the vertex. So each one of these angles was 120 degrees, and then it got cut in half into 60 and 60. In a square, those angles get cut from 90 degrees in a square at the vertex. It gets cut into 45 and 45. You can kind of see where we're going here. We're seeing some familiar numbers. 90 degrees, 45 degrees, 60 degrees. All right, we're going to use some special right triangles here. In some other cases, we can maybe apply some Pythagorean theorem. All right, and we'll explore that a little bit more. There's another segment that we could draw as the altitude of each one of these triangles. The altitude of each one of these triangles we refer to as something called the apothem. The fancy word here is apathem. The perpendicular distance from the center of our polygon to the side. All right? That perpendicular distance is referred to as the apothem. All right? Now this is very useful to us because I can draw that apothem in any one of these triangles, and that distance is the same as this distance, is the same as this distance, is the same as that distance, as long as we draw that segment perpendicular to the edge. So the apothem is smaller than the radius. Now how do we know that? The apothem is smaller than the radius because the radius in this situation is the hypotenuse of our right triangle. All right? The legs of our right triangle are the apothem, and then half of our side. Here's an interesting thing. Remember, these radii are all congruent. So these triangles are isosceles. And when I draw on that apothem, it is the perpendicular bisector of the base. You see how there's a lot of synthesis of these other skills and concepts, these other ideas that we've been wrestling with since Unit 3, Unit 4, Unit 6, Unit 7, which means that we can apply special right triangles in some cases, Pythagorean theorem perhaps in others, and of course the area of triangles to try to find the area of these regular polygons. The area of a regular polygon is found by taking half the product of the apothem and the perimeter. All right? Half the product of the apothem and the perimeter. All right? When we multiply those together, we are going to get the total area of this total figure. Essentially what's happening is this. The perimeter of any polygon is the number of sides times the length of each side. All right? And in this case, we have this strange situation where we have the apothem times the side length times a certain number of triangles. Well, let's think about this. The side length here is the base of one of these triangles. This is the side length. Whereas the height of each one of these triangles is our apothem. So what we're dealing with here is the number of triangles, in this case 6. If we had a square, it would be 4. If we had an equilateral triangle, there would be 3 of them. If we're dealing with a regular pentagon, there would be 5 of these triangles. Multiply by 1/2 base times height. Well, 1/2 times the base of this triangle, that's the length of each one of the sides, times the height of each triangle, that's the apothem. So essentially, these are all the same formula. It's just kind of streamlined using area equals 1/2 apothem times perimeter. Now, of course, finding the perimeter, we're going to not necessarily be given that information. We're going to take the number of sides times the length of each side. All right? And so we're going to get to do some fantastic math here in just a moment. All right? So let's go ahead and put this to work. This is just kind of the explanation of why this is the formula. If that bugs you or if that confused you, just go ahead and shoot me an email or bring it up in class and we'll chat about it. So we're going to use this formula to help us find the areas of some regular polygons. We're going to deal with some regular hexagons, some regular triangles, and some squares as well. So the squares are a little silly because we're like, why don't we, if we know the sides, we can just square the side, right, based on height there, or multiply it by itself. So we're going to do some fancy stuff here in just a little bit. But for each one of these, I'm going to give you a different piece of information. I'm going to start with one of these figures, and I'm just going to draw in our regular hexagon here, I'm going to draw in some key information for us. All right? When I draw in a couple radii, I want us to consider different scenarios that we may explore. I'm going to draw in an apothem into each one of these so that we have that as kind of our guiding portion of our discussion. And then I'm going to give you different pieces of information. All right, the first thing I'm going to give you is, what if I told you the length of the radius was, 8 centimeters? All right? In the next one, I'm going to show you that the length of a side is 8 centimeters. And then in this last one, I'm going to show you that the apothem is 8 centimeters. And these are all different examples, all right? Different given information, all right? We're given a radius, we're given a side length, we're given an apothem. And I'm using the same number every time so that we can kind of see the differences here, all right? So, again, the area is found by taking 1/2 times the apothem times the perimeter. Well, the thing that's very strange about this is that I don't know apothem or perimeter. I know that there's 6 sides, but I don't know the length of each side yet. And so this is going to require some problem solving and some thinking. But that's going to inform our the other parts of our conversation. So the first thing that I want for us to mention is that this is a hypotenuse, right? The hypotenuse in a right triangle, all right? If I'm just looking at this piece right here. So I can use that information to find other pieces of information here. But that's going to require me to do a little bit of thinking. The first thing I want to make mention is the measure of one of these central angles, all right? The measures of these central angles. The measure of this central angle, again, is 360 divided by 6, which in this case is 60, which in this case is 60. This whole thing is 60, but this 60-degree angle got cut in half, and so now this is 30 degrees, and this is 30 degrees. So when I drew in that apothem, I cut that angle, that 60-degree angle in half. So now I know that this is a 30-degree angle, a 30-degree angle, that this is a 30-degree angle, and therefore these triangles are 30, 60, 90. Now that also tells us something else that happened here. This angle was 60 degrees, or I guess the whole thing is 120, but then it got cut by the radius into 60 and 60, right? That's good information. This big blue triangle in every one of these situations is an equilateral triangle, all right? 60, 60, 60, 60, 60, 60, 60, 60, 60. So that means that we know that this segment is also a total of 8 centimeters, all right? If this side is 8 centimeters, that's given, then that means I know the radius is also 8 centimeters, all right? And we can kind of work from there. These two are the same situation. These two are the same situation. If I tell you the radius in a regular hexagon, that's also the same as giving you the side length in a regular hexagon. Now, that only applies with a hexagon. We're going to have some different things when we're dealing with squares and triangles, but this at least is a start to shorten our workload as we work between these two examples. All right? Now, even if we didn't apply that here, even if we didn't know that, we could still find out what this part of the base is, all right? Using 30, 60, 90 rules. The hypotenuse in a 30, 60, 90 is equal to the length of the short leg times 2. So in this case, 8 is equal to x times 2, or 4 is equal to x. If I know that this is 4, then I know that this is also 4 centimeters. So our total side length there is 8. So as I'm working here, I need to know what the apothem is, but I do know that the perimeter is going to be 6 sides times 8 centimeters each. I know what the perimeter is going to be, right? If they were 8, 8, 8, 8, makes 48 total. But I also need to find out what the length of the apothem is. The apothem is our long leg, which is the short leg times the square root of 3. So the apothem is equal to the short leg times the square root of 3. Oh, the apothem is 4 square roots of 3. So I can now compute this area by taking 1/2 of 4 times 6 times 8 times the square root of 3. Let your calculator do all that work for you. And that should give us, let's say 2 times 48 makes 96. And that is the area of this regular polygon. Area is 1/2 apothem times perimeter. If you are still listening, go ahead and write in capital letters, hot dog unicorn on your notes. Just do it, and then I'll address it later. All right. Now, so this is example 1. Let's do example 2. We're going to have the same situation happening over here, but we're going to go about proving this a little differently. All right, let's pretend that we don't know that those are both 8. If we know the side length is 8 centimeters, then that means that we can take this value 8 and we can cut it in half. When we draw that apothem, it cuts that side length in half. I don't need to know that these are 8, although they are. We talked about that earlier. What I want for you to do is find the apothem. Well, folks, we're going to find the apothem in the same way. The apothem is going to be found by taking the long leg is equal to the short leg times the square root of 3. So in this case, the apothem is equal to 4 times the square root of 3. Oh, that's my answer. Yay, I've got it. Now I can do my work. The area is 1/2 apothem times perimeter. The area is 1/2 times 4 square root of 3 times the perimeter, which is 6 sides, times 8 centimeters each. And so that means here we have 96 times the square root of 3 square centimeters. All right. So the math works out the same way, just approaching it differently. Having the radius means we know what the side length will be. Having the side length means we know what the apothem can be, all right? And we have the perimeter already. This is the tough one, all right? All right, this is a tough one because we need to make sure that we have this apothem, all right? And so given this apothem, we have to work backwards using simplest radical form to find out what this piece is. I don't know what this is going to be, but I know that I need two of them, or I need to double it once I find out what it is to know the whole side length. And then I've got to multiply it by 6 to get the whole perimeter. So make sure you understand that. If I know what this piece is, then I know the side length, and then I know the whole perimeter. All right? So we double it to get the side length, and then we multiply by the number of sides to get the total perimeter. But we've got a little bit of work to do. Remember, the long leg is equal to the short leg times the square root of 3. All right? So we've got a little bit of work here. And what we're going to do is take those 8 centimeters that we're given, and that's going to equal x times the square root of 3. We have a bit of division to do. Oh, no. And so the way that we will approach that is we will rationalize our denominator. All right? We will multiply this by 1 represented as the denominator over itself, which gives us 8 square roots of 3 over the square root of 9, which is 3. All right? So this is the length of this little piece right here, which means that 2x's is going to be 2 times 8 square roots of 3 over 3, which is going to give us 16 square roots of 3 over 3. All right, I know that algebraically, mathematically, arithmetically, whatever you want to say, that is difficult work because we're rationalizing denominators. If that's the only hardship that you're having with this, you're in good shape if that's the only issue that you're having. All right? But I want to make sure that you can see that you see another example of that worked out, and that you feel at least like you can understand what's happening. Once we know the side length, we already have the apothem, we can find that perimeter. All right, so the area is found by taking 1/2 apothem times perimeter, or 1/2 times 8 times the perimeter. The number of sides is 6 times the length of each side, 16 times the square root of 3 over 3. All right? So we've got a little bit of math magic that can happen here. I'm still going to end up using my calculator because it's going to make us feel a little bit groovy. But basically what we're going to have is 1/2 of 8 makes 4. 6 divided by 3 is going to be 2, so I get 4 times 2 makes 8. 8 times 16 should make 128, I believe. 8 times 16, yeah, it's 128. So we end up with the area is 128 times the square root of 3 square centimeters. You can use your calculator to type 1 divided by 2 times 8 times 6 times 16 divided by 3, and it will calculate all of that for you. You get 128. Tack on that square root of 3 if you're using a calculator that doesn't do radicals, and that will give you your total area. All right, so here was an example where we were working with special right triangles, 30, 60, 90. Example 1, example 2, example 3. And I really just want to do one more. Clock right now is at, it's at 20 minutes. Yikes. All right, so let's do this. Let's shelve the rest of this. I would love to do more, but what I want to do is, I'm not going to work through these examples. I'm just going to give you a little bit of guidance for examples 4 and 5. All right, that little bit of guidance for examples 4 and 5 is just to let you know what happens when we are working with these types of situations, okay? So this is the last piece that I want you to keep in your notes. Those radii are all congruent, so these are isosceles triangles, all right? But I want to make sure that we know the measures of our angles here. All right, so that you have that. So when we draw in our apathem, we are cutting these situations and making out of them, we're making special right triangles. And so we can use that information to work from either given the radius or given the side length or given the apathem, we can kind of navigate those different ways using and applying special right triangles. So those formulas of the long leg is equal to the short leg times the square root of 3 is going to be useful here when we're finding perimeter. Knowing that these legs are congruent to each other is going to be useful because once we know the side of the square, we can find the area. All right, or we can still use 1/2 apathem times the total perimeter. And so, the approach here, the hope here is that if you have this down for example 4 and example 5, you should be in very good shape. All right, now I want you to write at the end of the notes here, I want you to write Kansas City Chiefs and Kansas City Royals and Gardner Edgerton Blazers are my favorite team, all right? If that's a lie for you, then you don't have to confess if you like the Broncos or something. But what I would like for you to do is write down that you like the Kansas City Chiefs, you like the Kansas City Royals, and you like the Gardner Edgerton Blazers. And that will get you some extra love on your notes when you turn those in. All right, so hopefully there are no other issues. If you have any questions or concerns, we can address those together in class on our 7-5 day.